All right, so the next speaker is Alessandro who tell us about generative models for effective string theory.
Okay, thank you. So it's a pleasure to be here. So this is a work made in collaboration with Michele and Elia Cellini, and it's based on this paper here, which we put on the archive a couple of months ago. So Michele already gave a very nice and detailed description of the interplay between effective string theory and lattice gauge theory. So on one hand, for example, we can compute the expectation value of a polyacoulo colorator using lattice simulations, and we know that well, this in principle should be described by the effective string theory, in particular by the partition function, the effective string theory. Now, we know that this had an enormous success using the Lambo-Goto effective string theory, for example, and Michele gave lots of examples about it, but we know that, for example, there are other observables that we want to compute, and we perhaps don't have an analytical handle on these observables. The string width is one of these. I will mention it later. And also, we want to use more complicated actions for which analytical computations are also quite difficult. Now, the idea is actually quite simple. Why don't we try to do this numerically? So we do a numerical simulation of the effective string itself. So essentially, in the case of the Lambo-Goto that I wrote here, this will become a discretized version in this case. So we have essentially the scalar field, which is describing the transverse fluctuation of the flux tube, so of the worksheet. Now, why don't we try this? Of course, we impose these kind of boundary conditions in the time in the space direction. So we know that we have the two core-kinetic work, the two color sources. So, but the point is that if you want to do this and you use just a standard Monte Carlo, it fails. It fails because we have something which we call critical slowing down in the lattice community. And the idea is, for example, that if we want to increase the volume, but also if we put the string tension towards 0, which is where we want to go, the autocorrelation time of our simulation explodes. The autocorrelation time is something that we use to measure how essentially similar the sequence of configurations in our Monte Carlo simulations are. And essentially, if you go, for example, to small sigma, it's more or less where you want to go to compare with lattice simulations, you can see that you have to essentially generate thousands of configuration just to have two independent configuration of fields. In this case, it would be the field of the Lambo-Goto action. Now, the point is that we want to use a different approach, and Andrea already gave an example of this kind of approach in his talk, using normalizing flows. This is a so-called flow-based approach. The idea is, again, quite simple. We want to use a mapping, which is usually parameterized by neural networks, between the target distribution, which is the Lambo-Goto theory, in our case at small sigma, and some tractable distribution, which in our case will be essentially the free boson, something that we have a complete analytical handle on, and we can sample from, for example. Now, this has been quite a success if you keep yourself essentially in lower dimensional theories. For example, gauge theories in 2 dimensions, Schwinger model. There have been many examples by several people in this community. If you're interested, this is a nice review about it. But the point is that if you go to larger volumes, as Andrea was already mentioning before, there are issues. Now, the architecture that we actually use is called stochastic normalizing flows. It's a bit of a mix between non-equilibrium Monte Carlo simulations, which are based on this result here from non-equilibrium statistical mechanics that I will not be able to explain in this talk, and also with these flows, these normalizing flows, which are essentially neural network parameterized diffeomorphism that, for example, Andrea used in this talk. Now, this is roughly a sketch of the simulations we are going to compute. These, if you want, these black circles are, in our case, essentially configurations of the free boson, if you want. And then we kind of flow towards the target, which would be the red circles, by alternating some transformations that are parameterized by neural networks. We call them layers, coupling layers, and some non-equilibrium Monte Carlo updates. The Monte Carlo updates have to be non-equilibrium because essentially what is happening is that you start from sigma equal infinity here, and then you move in 1 over sigma until you reach the target sigma if you want, so where sigma is the string tension. And of course you have to do some training. If you want, like the orange points are the time transformation, and which have to be trained. And the training is done by minimizing a Kruger-Krabbe divergence. Now, a very cool thing about this is that you get, exactly as Andrea was explaining before, directly a partition function. And in particular, the partition function is exactly what we need. Well, it's not exactly what we need, but for sure it's a beautiful check that we do because we already know the partition function. So everything I said until now, we can check whether it makes sense or not. So if you look at the partition function Namogoto, where you can write it down, and in particular in the larger limit, you can see here the RLO, so the linear increase of log z. And again, so this is essentially our numerical setup. We know that we want to get this. So we tried, and these are the results. So the blue points both here and here for two different values of the string tension are our results, in particular for this combination of the coefficient of the essentially linearly rising potential. And you can see that it perfectly overlaps with an Namogoto analytical solution. And in particular, if you also do the computation for the free boson, you can see that you can clearly distinguish both of them. And if you, well, these points here, the blue points have been fitted, and these coefficient here of the fit essentially is compatible with pi over 3, which is exactly what we need from this guy. Okay, now can we do something more with this? We can, of course. We can compute the string width. And in this case, well, let me do it first what we want to do numerically. This is a snapshot of our lattice. This is the Dirichlet boundary conditions where the two quarks would be in principle. We do static quarks. And what we do is essentially compute phi squared on the midpoint between the two quarks. And we average this in time, and of course over all the configurations that we sample. We already know a few things analytically, even if it's not exact, because we have a perturbative calculation in 1 over sigma made by Gliozzi, Reve, and Wiese. And we know, for example, this is for high temperature, so relatively close to the confinement transition if you want. And we have this behavior for the linearly in R. And Michele and collaborators conjecture that you can resum this behavior in R in this way, and this is what we want to check right now. And we can actually do that. We compute this guy, we make this fit, and then we look again at this at the coefficient here again, so we fit again. And you can see that this behavior exactly corresponds with the one that is predicted by this conjecture here. So we essentially can check numerically something that we knew, but only by looking at lattice simulations. So in this case, we lattice gauge theory simulations. Now we already know, we can confirm it numerically, also looking directly at Namogoto. Okay, this is a snapshot of what we can also do for now qualitatively, but I think it's also quite important to mention it. We essentially made simulations at relatively large value of sigma, but including a term which is a kappa to the fourth term, which includes the curvature. Now, we did it both at the high temperature and low temperature. And here you can see essentially the effect of switching on the coefficient of the k to the fourth term, which is quite impressive. And we already also did the same for a k squared term. And in principle, this opens up many possibilities to do this also for more complicated theories. And maybe, yeah, I can really jump to my conclusions. So the idea is that this stochastic normalizing flow, in general flow-based approach, essentially provide you a tool to fight critical slowing down, which is very interesting for lattice people like us. And there is, for example, also we want to use this also for the SU3 theory, in particular to fight topological freezing. But Namogoto is essentially a particular laboratory in which to do this because we know many things analytically. We can check about whether this numerical approach makes sense, and it does. It works very well. It captures the phi details actually of the partition function, and we can also say something interesting about the string. And I didn't mention much about. We also checked, for example, the profiler flux tube. We calculated the Binder cumulant, which is an interesting way to see whether the profiler flux tube is Gaussian or not. And well, in principle, you can also look at more complicated observables, which will be quite difficult to study analytically. And of course, you can go to high dimensions, higher order terms, and so on and so on. So I think this is it. Thank you for your attention.
Yeah, Yeah, it's not that the number beta is not supposed to be a strictly well-defined theory. Do you see any sign of this?
I don't think. Well, perhaps I think you should if you had like if you increase the precision at some point, you should see it, but we don't see it.
What do you expect? What would you see that goes wrong?
Well, I mean, we do see some signs of non-Gaussianity, for example, in the profile of the flux tube. I think I might have something like this, but these might be related to the fact that we see finite size effects. I think these are the ones which are the
if you simulate the area actions in the Euclidean, you see these branched polymers or spikes.
We haven't looked at that, but we might. I think there is a lot of work to do.
Just a question from a technical point of view. I mean, do you encounter any limitations? I mean, hardware limitations?
Yes. Well, of course, when we looked at the calculated forms, for example, we cannot push a sigma to very small values. It's like a combination of critical slowing downs, all of them together. And but I think this is somehow. I mean, the approach should be the right one. The flow-based approach, if you manage to build such a map, in our case it's a mix of stochastic and deterministic, you should make it. I think this is, with better coupling layers, with a better understanding of the protocol. I mean, we're moving 1/sigma, which is kind of a TT-bar transformation, deformation. Maybe there is a better one, I'm not sure. I guess it depends also on the. I mean, you have to customize a bit your. But we do see limitations.
Other questions? Okay, no, let's thank Alessandro.